Okay, this is the last lecture covering relativistic dynamics. This is part 5. Specifically, we're going to take a look at an example. Go ahead and copy down the lecture example from the document in today's folder. Copy that down into your notes. Let me read it to you now. Okay, how fast would an object be moving with respect to a stationary observer if the kinetic energy is twice the rest energy? Okay, in order to approach this problem, we're going to take a look at this portion of the expression right here. So the energy E is the kinetic energy plus the rest energy. And we're specifically given the following. We're given that the kinetic energy K is twice the rest energy. So we're given that K is 2 times m0 c squared. So let's go ahead now and write that in here into the expression like so. And then add up the following on the right-hand side of the expression to obtain the following. That is this expression here. The left-hand side of the expression, E, of course, is mc squared. And it's now specifically here on the left-hand side of the expression that would replace the relativistic mass m with the following. Like so. And then what we solve for here very simply is V. When we do solve for V, we'll end up with a fraction or a percentage of the speed of light as the answer. So at this point, I just have to do a little bit of manipulation. Notice that the m0 c squared cancels, like so, and then just let me rewrite what is left over. That is this expression, like so. And now we have to solve for V. So let's go ahead and cross multiply these terms like so. And then let's go ahead and get rid of the radical sign here by squaring both sides. Like so. And now let's go ahead and solve for V. So take this term here and move it to the left. Take this term here and move it to the right, such that you then end up with this. Now the right-hand side of the expression there, 1 minus 1/9 is just 8/9. Like so. And now just cross multiply the c squared over to the other side of the expression, and then just take the square root now to get v by itself. And when you do, you end up with the following as the answer. So let me just go ahead and see what the square root of 8/9 is. That's equal to, there we go. It's about 94% the speed of light. It's about 0.94 c, like so. Okay, and then the last portion of the problem asks us to do the following, make a comparison. It says, compare the object's kinetic energy. Let me go ahead and reveal my file for myself here. It says, compare the object's kinetic energy to its classical kinetic energy by calculating a percent difference. Before I actually do that portion of the problem, however, remember, of course, from chapters 7 and 8 that the classical kinetic energy is just 1/2 mv squared. By now, you've gotten the idea that essentially everything that I've taught you up until this point in the school year has essentially been an approximation. What really happens, of course, are relativistic situations that we've been examining here in this unit. So 1/2 mv squared should be an approximation of what really happens. What really happens in the expressions here is the kinetic energy K. So now what I want to do is I basically want to derive for us the approximation of 1/2 mv squared before we actually get to the problem itself. So in order to do so, let me do some erasing here. Okay, so now let me ask this. Where does the classical kinetic energy come from? Well, let's start with the following. Kinetic energy K is mc squared minus m0 c squared. Like so, and relativistic mass m is the following. Like so. Okay, let's see what happens to this expression if V is small. If V is small compared to C, then we have classical physics as we've explored over the course of this year. In order to do that, however, let's specifically take a look at the 1 over the radical sign term. I'm going to do so here off to the side. Let's look at this guy right here, and let me rewrite this expression like so. Okay, take a look at this carefully. And now what I'm going to do is I'm going to apply to this expression something that you're all familiar with from your math classes. I'm going to apply to it the binomial expansion. Do you remember the binomial expansion? The binomial expansion was the following. Okay, here's how you saw it back in math class, where n is an exponent associated with this quantity. And then if you expand out this expression, the first two terms, that's all that's important for our purposes here, looks like this. And so on with the additional terms. However, we're only going to need the first two terms for the binomial expansion here in this expression because V is small. So now let's go ahead and apply the binomial expansion to this quantity. Okay, so when I do, this quantity here then becomes the following. First 1, and then I have a minus sign here, so minus, and then my exponent n, which in this case is -1/2, and then multiplied by my variable, v squared over c squared. I don't need any additional terms in the binomial expansion here because the next term would be in terms of a v to the 4th over c to the 4th. That number is extremely small, however, in classical physics when the speed v is small compared to the speed of light. So then therefore I only need these two terms. Okay, this simplifies a little bit. And the expression looks like this. So now let's replace over here the 1 over the radical sign with this, and then watch what happens when I do. Okay, so kinetic energy K is first of all the numerator, m0 c squared. And then the 1 over the radical is now this guy right there. Okay, and then minus the rest energy, that's that term right there. And now let's just go ahead and simplify. So I've got here m0 c squared times 1 minus m0 c squared, which drops out. And then I'm just left with this. Like so. Cancel the c squareds. And then you get this, the classical kinetic energy that we saw back in chapter 7. Remember, of course, there was no such thing in chapter 7 as relativistic mass. Everything was just in terms of the rest mass. I didn't say it as such, however, back in chapters 7 and 8. So then therefore, the classical kinetic energy is an approximation of what really happens. What really happens is the relativistic kinetic energy. Regardless, however, to finish the portion of the problem that we still have to do here, it now says the following. Compare the object's kinetic energy to its classical kinetic energy by calculating a percent difference. Once again, we'll do this as a percent error sort of calculation. Okay, let me go ahead and do some erasing here. Okay, so the percent difference that we're going to calculate is the following. First of all, we have here the relativistic kinetic energy. Okay, now the M, I'm going to go ahead and immediately write like so. Okay, and then we're going to subtract from that then the classical kinetic energy, like so. And then we'll divide by the actual value, if you will. The actual value of the kinetic energy is the relativistic. Like so. And now what I'm going to do is plug in for V here, here, and also here, the answer that we found earlier from part A, or the first part of the problem, where the v, if you recall, was 94% the speed of light. Okay, I'm going to do some simplifying here, however, as I go. So in order to do so, first, let's go ahead and cancel out an m naught here from each individual term, like so. Okay, and then let's now start to go ahead and replace the v's with the 0.94c. Okay, so my percentage then is going to be the following. Okay, first of all, in the parentheses in the numerator, I've got 1 over radical 1 minus 0.94 squared. The c squareds will all cancel out. Okay, and then minus c squared, like so. There's a c squared up here in the numerator, excuse me, like so. Okay, and then minus 1/2 times v squared. So minus 1/2 times 0.94 c quantity squared, and then divided by this same parentheses right here. Like so. I just wanted to make sure that I wrote this out correctly. Okay? Okay, now this is kind of a mess, as you can see, but if you do take a look carefully in each term, notice that a c squared is present. There's 1 here as well. So now all the c squareds will drop out. So let's get rid of all of that. This is a 1. This is a 1. And this c is now gone as well. Okay, so let's go ahead and write this whole mess out now. All right, so I'm going to do my calculations. So I first of all have 1 over the radical. Let's clear that. So 1 divided by the square root of 1 minus 0.94 squared. Okay, that comes out to be about 2.93. 2.93. Okay, and then minus 1. Okay, and then minus this guy here. So 1/2 times 0.94 squared. Okay, that comes out to be about 0.44 or so. Like so. And then the denominator of this guy here was the same as this. It was 2.93 minus 1. Like so. And then I'll take this whole thing and I'll multiply it by 100 in order to convert it into a percentage. All right, so let me go ahead and finish this up. So 2.93 and then minus 1 minus 0.44. And then all over 2.93 minus 1, so 1.93. Take that, multiply it by 100, and it ends up being a 77% difference. So then therefore, if we were going to do an energy calculation for an object that was moving at this speed relative to a stationary reference frame, we would have to write kinetic energy in its relativistic form, definitely not in its classical form. Okay, that concludes the lectures here on relativistic dynamics.